Hi everyone, this is digital filtering using FPGA. Digital filters use a digital processor to perform numerical calculations on the values of the signal. In our project, we implemented two types of digital filters, convolution, which convolves the signal with an impulse response, and a second order section, which is similar to convolving with impulse response, but uses additional output data as well. So the block diagram, an unfiltered signal is generated in MATLAB and transmitted serially through UART and a FIFO buffer for temporary storage to our Verilog FIR filter. The signal reaches a mux, which is then used to select between the SOS filter or the convolution filter. We weren't able to implement the mux, so we are manually currently selecting between the two modes. The filtered signal is then transmitted back to MATLAB through a first in, first out buffer and UART.
Filtering using convolution. In this convolution process, the input signal is delayed by n intervals, as illustrated in the diagram with x of n minus 1 and x of n minus 2, indicating two-step time delays. Each delayed input is then multiplied by specific coefficients. These products are then summed using full adders, as shown in the slides, facilitating the state machine's computation and outputting the convoluted signal one value at a time. We're able to use n number of coefficients and n number of bit widths of the coefficients.
As we can see, here is the convolution filter. As we can see, there are two parameters, n equals 4 and data width equals 8. N is the number of filter coefficients and data width is the bit width of the input and coefficients. As you can see below here are the coefficients inputs, and here is the shift reg where it delays the x and inputs by 1. This is like the DFF part. Then as you can see, there's a product where this product variable would multiply the shifted delayed x and variable corresponding to its coefficient. And the sum would add up all these values together to produce the output. As you can see, these are the inputs that we have for now. 4 for n and data width is 8. And the coefficients are -4, -2, -1, and 0.
So we'll move on to our test bench next. The third row shows our input signals, which are 2, 4, 8, 16, and 32. And the row right after shows our outputs, which is -8, -20, and so on. And that matches with the values that we had predicted. Now Heewon's going to go back and change up a few of our parameters as okay, so Heewon changed the parameters to 0, 0, 10, 0. And what this does is that it delays the output by 2 values, and it also scales up the values by 10. And since we're scaling the values by 10, we need to represent the numbers with a larger bit, which is why we changed the bit size to 16. Now moving on to our test bench. So our test bench does corroborate our initial hypothesis. We can see that for our first value, which is 2, the corresponding value is 20. It's indeed been scaled by 10, and there's also a delay of two values.
This is an FI filter, implemented using second-order section design. The filter processes an input signal xn to produce a filtered output y, using predetermined coefficients betas and alphas. The structure uses two previous inputs, xn-1 and xn-2, and two previous outputs for filtering. Input values are delayed through D flip-flops to provide these past inputs. Each coefficient multiplies in corresponding input or output, and results are summed using full adders. Key features include coefficients are fixed 5 coefficients, but the user can modify the coefficient's bit width. The filter combines past and current inputs to calculate y efficiently using simple arithmetic operations. This structure is a modular and ideal for implementing FI filters in hardware where precision and stability are crucial. This is an FI filter, implemented using second-order section design. The filter processes an input signal xn to produce a filtered output y, using predetermined coefficients betas and alphas. The structure uses two previous inputs, xn-1 and xn-2, and two previous outputs for filtering. Input values are delayed through D flip-flops to provide these past inputs. Each coefficient multiplies in corresponding input or output, and results are summed using full adders. Key features include coefficients are fixed 5 coefficients, but the user can modify the coefficient's bit width. The filter combines past and current inputs to calculate y efficiently using simple arithmetic operations. This structure is a modular and ideal for implementing FI filters in hardware where precision and stability are crucial. As you can see, this is the FI filter, and this has the same parameter as the convolution filter. And looking at the bottom, we can see the coefficient inputs similar to the convolution filter. Then we see the delayed portion of the code, which delays the x by 1, and it delays it twice, so it would produce xn minus 1 and xn minus 2. Then the product would multiply the delayed x corresponding to its coefficient, then the sum would add everything together to produce the output. We can also see truncation on the bottom right here. The truncation would truncate it back to 8 bits, or the corresponding bits that it was taking the inputs in.
Yeah, so now moving on to the test bench, what we expect is for the output to be delayed by 2 and multiplied by 2. And if we look at the third and fourth row, our initial output, the input is 2 and the output is 4. For the input that's 4, the corresponding output is 8. And so we can see that the test bench does work, but there still are some concerns with the code. The previous code was properly, we were able to adjust the parameters accordingly, but this code is just not as adjustable yet. And this results in truncation errors on the FPGA.
So now to talk a little bit more about the UART. UART, or Universal Asynchronous Receiver Transmitter, is a serial communication interface that sends and receives data 1 bit at a time over a single data line. It consists of key components such as the baud rate generator for setting the transmission speed, a transmitter and receiver for handling data, and FIFO buffers for temporary storage. In our implementation, we've added a unique functionality, flags and physical buttons for manual control. On the receive side, the UART detects incoming data and raises the RX done tick flag once the data is reconstructed and ready in the FIFO buffer. The user then presses a button to retrieve this data, ensuring precise control. On the transmission side, the data is then written to a TX FIFO by pressing a write button. The UART transmitter begins sending the data with a start.
So now we're going to go over our
bits.
UART top
A
module.
TX done tick flag
that
so the
you can see
transmission is
here.
complete.
So we have a
This
few
button and
input
flag
parameters.
integration
So
makes your
here
UART
are a
system
few
highly
important ones.
controllable
I'll talk about
and great for
debits.
testing
So
and
debits is
debugging,
the
allowing
number
you to
of
monitor
data
each
bits
step
moved
of the
forward.
process. So for
Manually.
example, if you're doing UART communication with an 8-bit protocol, then your dbit value needs to be 8. Some additional inputs are the clock, buttons, resets, etc. But a few ones I want to point out is the read UART button and the write UART button, which are seen here. So these will read data in from the buffer when set to high, and then the write button will read data from the buffer to the transmitter pin and sending it back to MATLAB. So currently these two inputs are configured to be buttons or switches, and they allow the user to essentially have manual control over what's being read in and what's being read out. So just to go over some structure of the code, those buttons, as you can see, have been debounced to ensure that there's no debouncing concerns or errors. Once we do that, we actually instantiate and generate the baud rate. So basically this takes in our 100 megahertz clock, and knowing the baud rate, which is defined above, it'll actually output a signal that will generate and allow the rest of the code to operate based off of this baud rate. And then we'll also instantiate our receiver module and our transmitter module. Both of them are structured very similarly, where they take in a clock, reset, and then they're tied to the receiver pin on the FPGA, and they'll also take in the ticks. So these are essentially when it needs to sample that receiver line. This data will, when it's done, RX done tick will be raised to high, indicating your data out, which is stored in RX data out, is ready to be read and sent into the FIFO. Similarly, the UART transmitter works in a very similar fashion, but instead of reading data out, it is meant to read data in, meaning your TX FIFO not empty will essentially trigger reading. And then here we've just instantiated those FIFOs with the right sizes. So in this demo, we're going to show you our FPGA-based system integration UART module. So in this demo, you'll see FIFO buffers and the SOS filter for real-time signal processing. The system is controlled using a switch, which triggers at specific actions on its rising and falling edges. On the rising edge of the switch, the data from the UART module is sent into the RX FIFO, causing the data to push into a sequential filtering logic. This logic is implemented using an SOS filter configured to perform simple convolution operations. But however, you'll see that the output in MATLAB, as it prints out, from the filter does not match the expected results based on the programmed SOS components. On the falling edge of the switch, the system pushes the data into the TX FIFO and then triggers the UART transmission to send the data back into MATLAB for further analysis. This highlights the need to address overflow conditions to ensure accurate filtering to improve system performance. As Heewon highlighted in the test bench for this module, we are having issues with the buffers not being large enough to properly represent and store the numbers, causing it to output the number just scaled by 2 instead of actually multiplying by the stored coefficients. I hope this was a helpful video in understanding how digital filters can be implemented using UART and convolutions on a FPGA using hardware description language such as Verilog. Thank you.